Hi everyone, welcome to the new lecture of the mini course Computational Mathematics. Today we will concentrate on two subjects. First of them is how to find a bound for roots of a given polynomial. So we want to find a number such that all the roots sit in a disk on a complex plane in a disk with a computed radius. Second problem that we will tackle is the problem of counting and isolating roots of polynomials, most precisely real roots of polynomials. There is a number of algorithms that can do this. You will find some of them in the lecture notes. The link to the lecture notes is down below the movie. Today I will present one of them, in fact the most classical one, namely Sturm theorem. Sturm theorem returns the exact number of roots of a given polynomial in a specified interval. So once we provide a polynomial, we provide a real interval. Then, using Sturm theorem, we will get an exact number of distinct roots that this polynomial has inside this interval. So these two subjects will be dealt with today. Let me start with a definition of the problem that we want to deal with today. So let us assume that we are given a polynomial f, and the problem is to find some number m, capital M, such that every root psi of f is positioned inside a disk of a radius m. That's the first problem. The second problem, which is actually a dual problem to the previous one, is to find a number lowercase m such that there are no non-zero roots of f inside a disk of a radius m. So every non-zero root of f must be outside this small disk m. And the special case of this problem is when we do not concern complex roots, but we concentrate only on real roots. Then we are looking for two numbers, m plus and m minus, such that every real root psi of f belongs to the interval with endpoints m minus m plus. As I said, the first two problems are dual to each other, and this can be easily observed when we consider a reciprocal polynomial of f. So if f is a non-zero polynomial with coefficients f0, f1, and so on up to fn, then we define it a reciprocal polynomial by just taking f on 1 over x. Of course, if we compute f on 1 over x, if we evaluate this expression, in general, we will not receive a polynomial. This will be a rational function. So we make it into a polynomial just clearing the denominators. So we multiply this rational function by the greatest denominator which appears, which is clearly x to the nth power, because if we substitute here 1 over x, then we have fn times 1 over x to the nth power. So if we multiply it by the greatest denominator, what we get is again a polynomial. And if we just imagine how this expression looks like, then we'll have fn 1 over x to the nth power times x to the nth power, so this x to the n, so this nth power of x will cancel, and we'll have just fn, and so on and so on. Let's look at this expression. Now we have f1 times 1 over x times the nth power of x. So this nth power of x will cancel this 1 over x. So what we get is f1 times the n minus first power of x. And here, when we had a constant term, when we multiply it by the nth power of x, we will get f0 times the nth power of x. So all in all, the reciprocal polynomial looks like this. This is just the reciprocal polynomial of f. What we did is actually we inverted the list of coefficients. So what was the constant term is now the leading coefficient. What was the leading coefficient is now the constant terms. So the two reciprocal polynomials have the same lists of coefficients, but in the opposite order. So if f is f0, f1, and so on up to fn, then reciprocal of f is fn, fn minus 1, and so on up to f0. Because we constructed the reciprocal polynomial by just inverting the variable, the easy observation is that the roots of the reciprocal, of course non-zero roots, are just the inverses of the roots of f. So consequently, if m is an upper bound for the roots of the reciprocal polynomial, so the roots of a reciprocal polynomial are the inverses of the roots of f. So if m bounds the inverses of roots of f from above, then the inverse of m must bound the absolute value of non-zero roots of f. So all in all, if we know how to compute the upper bound for the absolute values of roots of a polynomial, at the same time just inverting the list of coefficients, we can, and inverting the upper bound, we got the lower bound from absolute values of non-zero roots of f. So if we return to our list of tasks, we see that it's enough if we devise a method to solving the first task, because if we have it, we automatically have a method to solve the second task. So these two tasks, as I said, are dual to each other. If we know how to solve one of them, we know how to solve the other one. Historically, the first ever bound for roots, as far as I'm aware, appeared in the book by Cauchy in the first half of the 19th century. So this Cauchy theorem says that if we have a polynomial with coefficients f0, f1, and so on up to fn, then for any root of this polynomial, any root psi of this polynomial, we have such an inequality. We have an upper bound for the root of polynomial in the form 1 plus maximum of this absolute value of fj over fn. If we look carefully at this expression here, we observe that these fractions here are just the coefficients of normalized version of f. So if we normalize f, if we make f monic, so if we divide by fn, then this will be the roots, these will be the coefficients of the monic polynomial obtained from f by normalization. Of course, normalization does not change roots of a polynomial, so if we can always normalize f, it will not change any roots, and this is obvious that any bound for the roots mustn't be influenced by normalization. So this is why we have here this fraction, so the coefficients of a normalized polynomial. Let me now show you how we can prove this theorem. The proof is actually very easy and quite short. We will consider two cases. So let us consider two cases. First, we assume that the absolute value of psi, so the absolute value of our root, is less than or equal to 1. If this is the case, then our assertion is trivial, because if we look here, then if this does not exceed 1, then of course the right hand side is of course greater than 1, because we have 1 plus something something positive. At least one of the coefficients must be non-zero, so this part is definitely positive, so we have 1 plus something, so this right hand side is greater than 1. So if the absolute value of psi is bounded from above by 1, then of course this whole formula holds. So this part is trivial. This is 1, and 1 is strictly less than 1 plus something positive. Something positive. So in this form, the formula, the assertion of the theorem holds in this case trivially. So the only part which we need to prove is the case when the absolute value of psi is strictly greater than 1. So that's the case that we need to consider. Now, what we know? We know that psi is a root. Psi is a root of f. So this means that 0 is f of psi, but well, we have a explicit formula for f. So this is f0 plus f1 psi plus and so on and so on and so on, plus fn minus 1 psi n minus 1 plus fn, and now we have the nth power of psi. So we can write the nth power of psi in the following way. The nth power of psi is minus f0 over fn minus f1 over fn times psi minus and so on minus fn minus 1 over fn times the n minus first power of psi. Now I compute the absolute value of both sides. So this means that the nth power of the absolute value of psi is equal to this minus sum. Of course, minus has no meaning when we compute the absolute value, so it's I strictly less than n fi over fn times the ith power of psi. So this does not exceed the absolute value, the sum of I less than n, the absolute value of fi over fn times the ith power of the absolute value of psi. Now I will denote by m the maximum of these fractions that appears here, so it's fi over fn for I strictly less than n. So with this notation, I can write that the nth power of the absolute value of psi is bounded from above by, and now every term here can be bounded by from above by m. So this absolute value of psi does not exceed, and now I will have m times sum for I strictly less than n, ith power of the absolute value of psi. But now if I look here, this guy here is a sum of geometric series, and this is a finite geometric series, so we can actually explicitly write the formula for this sum. So from what we know about geometric sequences, this is nothing else but m time, and we have we started indexation from 0, and and the indexation runs from 0 to n minus 1. So there are n terms here of this sequence. So this is absolute value of psi n minus 1 over absolute value of psi minus 1. So what I want to do now is I want to compare the left hand side and the right hand side of our expression. So what we have proved is that the absolute value of psi, the nth power of the absolute value of psi, is bounded from above by m times the nth power of the absolute value of psi minus 1 over the absolute value of psi minus 1. Now, let us look back at our assumption from the very beginning of the proof. Here, we assumed that the absolute value of psi is strictly greater than 1. So if we look back here, the denominator of our fraction is strictly positive. So from the assumption, it follows that this is greater than 0. So we can multiply both sides. Of course, the left-hand side is also strictly positive. So we can multiply both sides of our inequality by the following positive expression. And what we get is that absolute value of psi minus 1 is bounded from above by m times the nth power of the absolute value of psi minus 1 over the nth power of the absolute value of psi. But now, this whole fraction, the numerator is strictly smaller than the denominator. And of course, both the numerator and denominator are positive numbers, but the denominator is greater than the numerator. So this whole fraction is strictly less than 1. So this is strictly less than m times 1. Of course, m times 1 is 1. So if we now look at this part and this part, what we get is that the absolute value of psi is strictly less than 1 plus, here is m, 1 plus m. And this proves our theorem. So this is the proof of the Euler theorem. So this was the first bound for the roots of polynomials. As I said, this was due to Cauchy. In fact, in the very same book, Cauchy proved also another bound for the roots of polynomials, and this says that again under exactly the same assumptions, when the absolute value of the root is bounded from above the maximum of the expression over for n times the fraction fj over fn. This is exactly the kind of expression that we encountered previously. So this is the coefficient of a normalized polynomial, of a monic polynomial obtained from f, and we understood already why it's here. But look at the exponent is 1 over n minus j. So the denominator in the exponent is the difference between the indices in the denominator and the numerator of the expression. This is quite important for us because we will shortly observe that the formulas of this kind also appear in the other bounds for polynomials. Also, they are also present in these more modern bounds for polynomials. I will omit the proof of this theorem on today's lecture because we don't have enough time. However, the uh, proof for the proof C, the lecture notes, CM, the link to the lecture notes is as always below the movie in the section below the movie. This proof is not complicated. It's not very long, and it's not there is nothing fancy about it. I just don't have enough time to prove every theorem that I present here. And so I will concentrate on the most important one. As you can see, these oldest bounds due to Cauchy are now almost 200 years old. Of course, the development of mathematics didn't stop in the 19th century. So, in the meantime, many new results were developed and invented, were developed for bounds of polynomials. Uh, in particular, some results are some kind of meta theorems that don't really give an explicit bound, but instead they provide a method for constructing such bounds. In the lecture notes, you will find two such methods. One is due to width, and it is designed to construct bounds for the complex roots of polynomials. The second such a meta theorem is due to Stefanescu, and it is specialized for constructing bounds for real roots of polynomials. I will present now this Stefanescu theorem, but before I do that, I need to introduce a new term. We will say that a polynomial f is written or presented in a balanced form if we write it in the following way, that it is a sum of such binomials, gix to epsilon I minus hix to the ei, such that all these coefficients gi and hr are strictly positive, and the exponent at gi is strictly greater than the exponent of ei. So in every parenthesis we have a monomial, we have a difference of two monomials such that the coefficients of both monomials are strictly positive, but the exponent of the first monomial is greater than the exponent of the second monomial. And in addition, we may have some additional polynomial with non-negative coefficients. Because all the coefficients of R are non-negative, it follows that R cannot have any positive roots. So this R can be here or it can be zero, it doesn't matter. We say that the coefficients are non-negative, so if R is zero, then it's okay. The important part is this one, the sum of these binomials. And the first observation says that the polynomial can be expressed in a balanced form if and only if the leading coefficient of f is strictly positive. So let me prove this. First, assume that the leading coefficient is strictly positive. So Fn, which is a leading coefficient of f, is strictly positive. Write J, the capital J, for the list of indices strictly less than n, such that Fj is negative. So we write J for the list of indices of negative coefficients of f. Now we can write f, or maybe I will add, in addition, I will denote the number of elements in this set by lowercase. Okay, So now f can be expressed as a sum. F is a sum for j in this set j. So we are summing over all the negative coefficients of f. And now we have fn over k times x to the times the nth power of x minus fj times the jth power of x. This takes care of all the negative coefficients, so everything which is left are positive or at least non-negative. So plus sum over j less than n, j not in j, f j x to the jth power. So this is our polynomial r. So as you can see, this is clear that this is a polynomial f. We express the leading term of f as a sum of k such monomials. So we use one such monomial for every term of f with negative coefficient. So it is clear when this is f and it is a balanced form of f. It is a balanced form. Balanced form. So this proves one implication. The other implication is quite clear, because if the leading coefficient is negative, so there is no way. So if the leading coefficient is negative, there is no way we can write some gi to x to some power where this power would be greater than the degree of a polynomial. So if the leading coefficient is negative, it would be one of those guys, but then there is no guy here that would have the greater exponent. So if here we have already the exponent is already the degree of f, so there is nothing we can write here. So it is clear that then the leading coefficient must be positive, and we have already proved that if it is positive, then such a balanced form exists. Of course, this assumption is not restrictive in any way, because the roots of polynomial will not be altered if we replace f by minus f. So if we have a polynomial and its leading coefficient is negative, we can always replace f by minus f, and now we will have a polynomial with a positive leading coefficient. So this observation does not lead to any problems. So we can always find a workaround. And now we are ready to present the Stefanescu theorem. This is quite a modern theorem. It was proved for the first time around 15 years ago. It says that if a polynomial is expressed in a balanced form, and we take expression of this form, so this is a maximum over all these parentheses, and here we have a fraction. In the numerator we have this coefficient, in the denominator we have this coefficient, and the exponent, as in the Cauchy theorem, is 1 over the difference of the exponents of the variable x that corresponds to hj and gj. So it turns out that this expression is the upper bound for the real roots of f. So if we can express a polynomial in a balanced form, so any way we express a polynomial in a balanced form, any method of expressing a polynomial in a balanced form gives rise to some bound for the roots of for the real roots of this polynomial. And now I will show you a proof of this theorem, which is actually quite simple. First, observe that this m is clearly positive. It's a maximum of some positive numbers, so it is positive itself. Fix any xi strictly greater than m, and we want to evaluate f at xi. So f at xi will be the sum of so f of xi is a sum of a form g j xi epsilon j minus h j xi e j plus r of xi. Of course, this guy is non-negative, and we will observe how this guy looks like. So our expression gj xi to the epsilon j power of xi minus hj ej power of xi can be written in the following way. This is the ej power of xi times gj. So now we'll have xi epsilon j minus ej minus hj. And now we know that xi is strictly greater than m. So this whole expression is greater than m ej times gj m epsilon j minus ej minus hj. But now recall what m was. If we look here, and we recall the definition of m. We have a definition of m, so we can replace m by this expression. So m is the maximum of this. So if we replace m by this expression, we will not increase the absolute value of our expression. So this is greater than or equal to m ej times gj, and now this is hj over gj because the exponents here and here cancels. The exponents cancel, so we have just this guy minus hj, and this is clearly 0. So if we now look at the left hand side and the right hand side, we have this guy, we have strict inequality, and we have 0. So this says that gj xi epsilon j minus hj xi ej is strictly greater than 0, but this means that f of xi cannot be 0. It's non-zero. And so what we have proved is, if we take any xi which is greater than m, then it cannot be a root of f. So by contradiction, any root of, if anything is a root of f, then it must be bounded from above by m. So this proves our theorem. So this is the proof of the theorem of Stefanescu. Let me present some examples, because in fact the quality of this bound heavily depends on the balance form of our choice. So I will consider the following example. Let f be a polynomial. Of course, we know that the leading coefficient must be positive, so let's say that it's 5 7th power of x minus 6x6 minus 3x4 plus 9x cubed minus x squared plus 10x minus 5, let's say. So a balanced form of f can be written in different ways. So one way would be to write f as I did before. So let me observe which terms have negative coefficients: 1, 2, 3, and 4. So these are the four terms of a with negative coefficients. So I can write f in the following way, that it is 5 over 4 x7 minus 6x6 plus 5 over 4 x7 minus 3x4 plus 5 over 4 x7 minus x squared plus 5 over 4 x7 minus 5 plus the remainder would be 9x cubed plus 10x. And so the bound is maximum of, and we'll have 6 over 5 over 4 to the power 1 of 7 minus 6. And now the other one will be 3 5 over 4 and 1 over 7 minus 4. And now the next one would be 1 over 5 over 4 and 1 over 7 minus 2. And here we have, okay, 5 over 5 over 4, 1 over 7 minus 0. So this is maximum of, and here we have 24 over 5. Here we have 12 over 5, and we have cube root of that. Here we have 4 over 5, and it is the fifth root. And here we have 4 and 7 root of 4. So it is quite clear when the maximum is here. So this is 24 over 5. So this balanced form give rise to implied this upper bound. But we can write f in a different way. We are not restricted to one balanced form. So alternatively, we can write f in the following way. So of course we need to use this term for these two guys, but here we can use other terms. So we can divide 5, we can split 5 in a different way. So we will have not 5 over 4, but let's say 5 over 2 or something else. So we can write it as 5 over 2x7 minus 6x6 plus 5 over 2x7 minus 3x4 plus 9x cubed minus x squared plus 10x minus 5. And as you can see, this is again a balanced form. This is just another balanced form.
And this another balanced form uh, implies another bound for the real roots of this polynomial f. So m plus now is maximum, and we'll have 6 over 5 over 2, and the exponent is again the same, so 1 over 7 minus 6. Here we have 3 over 5 over 2, and the exponent is 1 minus 7 minus 4. And when the next two terms differ, and we have 1 over 9 and 1 over 3 minus 2, and here we have 5 over 10, 1 over 1 minus 0. So this is a maximum of the following numbers. So it's 12 over 5. Here we have 6 over 5, and this is a cube root. Now we have 1 over 9, and 1 half. Again, the first term is the greatest one, but it is half of the previous term. So now we got a much better upper bound for the roots of polynomial. So the same theorem, the same Stefanescu theorem, but used with two different balanced form of the same polynomial, give rise to two completely different upper bounds for the real roots of this polynomial. So as you can see, everything depends how well we can convert a given polynomial into a balanced form. I will present two real bounds for polynomials that follow from Stefanescu theorem. In fact, the second one was proved before the Stefanescu theorem, but it can be proved using the Stefanescu theorem. The first one is local max bound due to Viglas, which was invented 10 years ago in Viglas' PhD thesis. In fact, in his PhD thesis, Viglas presented 4 different algorithms for computing bounds of real roots of polynomial. This is one of these 4 algorithms. This algorithm works like this. We take a polynomial and we initialize the local maximum. Of course, the leading coefficient must be positive. If it is not positive, we will replace f by minus f, so we make sure that fn is greater than 0. So we start with the leading coefficient here, with the local maximum here, and we start with exponent 1. And we scan this polynomial coefficient by coefficient, and depending whether a coefficient is positive or negative, we have two possibilities. So we have a loop over all the coefficient, and we take the jth coefficient, so we take the coefficient fj, and now as I said, there are two possibilities. Either this fj is positive or it's negative. If it is negative, we update the bound for these roots. So in fact, we write another term of our balanced form. We take the local maximum, this local maximum which was the leading coefficient, but it might have been updated in the meantime, and we take this local maximum and we divide it by the successive power of 2. So we have fi over 2t, and because this is in the denominator, we can write it here, and this negative coefficient here, and of course this exponent which follows from Stefanescu theorem. So this updates the bound for the roots of a polynomial. Otherwise, if it is not, if this coefficient is positive, we compare fj and fi, and we check which one of them is bigger. And if this coefficient is bigger, when we replace the local maximum by this fj, and we reset the exponent. In Instead of presenting a proof of this of correctness of this algorithm, which is quite straightforward, let me do one example. So I will take the following polynomial, say 10x5 minus 4x4 plus let's say 12x cubed minus 6x squared plus x minus say 5. So how does this local max works? This whole algorithm is equivalent to writing this polynomial in a balanced form in the following way. So first, this is our first local maximum. So our t is 1 and our maximum is 10. So we just scan the coefficients of a polynomial. So we start here. Now the first term here is here. This is negative term. So we just write fs 10 over 2 to the power t when t is 1 x5 minus 4x4, and now our t is 2. Now we take another term. Another term is 12. So we compare, it's positive, so we compare this guy with this guy. Of course, 12 is greater than 10. So our new local maximum is no longer 10, but it's 12, and we reset t to be again 1. So our local maximum moved from here to here. So this is our local maximum, and we scan another term of this polynomial, this guy here, and again we have a negative coefficient, so we write it as 12 over the next power of 2, and t is again 1, so it is 2 1 x cubed minus 6x squared. And we scan another term of our polynomial. This is x. This is again positive, so we can compare the coefficients. Here we have 1, here we have 12. 12 is greater than 1, so we do not replace the local maximum. We are here. And of course, I should have updated here because we have used already one of the exponents. So we skip this guy and we get here. And so we have 5. So we write our local maximum is 12. We write another exponent of 2, which is 2 because t is now 2. X cubed minus 5. And we write all the terms that we didn't use here. So this is 10 over 2x5 plus 12 over 4x cubed plus x. This is our polynomial r. So our maximum now, m, is maximum. The upper bound for the real roots is 4 over, here we have of course 5, this is 5, so 4 over 5 to the power 1, 5 minus 4, the exponents is 1 over 5 minus 4, and now we have 6 over 6, and the exponent is 1 over 3 minus 2. Now we have 5 over, here we have 12 over 4, so it's 3. So 5 over 3, and the exponent is 1 over 3 minus 0. So this is a maximum of 4 over 5, 1, and the cube root of 5 over 3. It's clear then this guy is the greatest one, so this is cube root of 5 over 3. So this is how the local max bound works. Let me now present another bound for the real roots. This is Hong's bound. The Hong's bound was invented in 1998, so as you can see, it predates the Stefanescu theorem. However, the easiest way to prove this bound is using the Stefanescu theorem. This bound works like this. We just, unlike the previous bounds, we have here a double loop. We have a minimum and maximum. So it works like this. For every negative coefficient, so when we scan this polynomial, we take every negative coefficient here, and for every negative coefficient, we consider all the positive coefficients with higher indices, and we take again this expressions which appear in the Stefanescu theorem. So the Hong's bound, which is one of the best bounds known for polynomials, says that every real root of a polynomial is bounded from above by this expression. Let me present a proof of this theorem again. We'll do it in the following way. Let me again write J for the set of indices corresponding to negative coefficients. So this is set of this J less than n minus 1, less or less than n minus 1, such that Fj is negative. And for J in J, write Mj for an index k such that remember that in this Hong's bound we had minimum of all these indices such that the minus fj over fk and 1 over k minus j, all right, for index k greater than j, is the minimum for all I greater than, okay, here is j, I greater than j, minus fj over fi, 1 over I minus j. So this mj is actually the index which corresponds to this minimum which appears in Hong's bound. So now we can write the polynomial f, write f in a balanced form, as follows. So we write f to be the, again like before, it is a sum of all j in this capital J, and here we have fm of j over 2 to the power m of j minus j times x m of j minus fj xj plus some non-negative, polynomial with non-negative terms, polynomial with non-negative coefficients. So all the other guys which are not really important for us. So by Stefanescu theorem, m plus the upper bound for the real roots of f can be computed as the maximum for j in j, and now we have okay, here is plus fj, so here is remember that fj is negative, so we need to have a difference of two monomials with positive coefficients, so we must replace fj by minus fj. So it is minus fj over fmj over 2 to the power mj minus j, and everything is 1 over mj minus j. Okay, but if we look here and here, we see that this expression in the exponent cancels, and we have maximum for j in j 2 times minus fj over f m of j, and the exponent is 1 over mj minus j, and now this is nothing else but this is maximum. Okay, we can write 2 here, this is j in j, and now recall what was the mj. The mj was expressed here. The mj was expressed here, so this is this minimum. This is exactly the minimum which appears in Hong's bound. So this is minimum for k greater than j, and here we have this guy minus fj over fk, and the exponent is 1 over k minus j, and this is exactly the Hong's bound. So we have proved this theorem. If we look at the previous bounds, the Cauchy bound and the local max bound, it was clear when the bounds can be computed in a linear time, because we have just, in all three of them, we had just one maximum. So we scanned the list of coefficients just once, it was all. On the other hand, if we look at the Hong's bound, here we have a maximum of a minimum. So in a straightforward, naive implementation of this bound, we will have two loops, loop inside a loop. First, we loop over all the coefficients of f, and we ignore the positive ones, but we scan all the, nevertheless we scan all of them. And then for every negative one, we scan all the coefficients, again, all the coefficients with greater indices. So we will have a double loop, and it looks like quadratic complexity. In fact, the straightforward, naive implementation of this bound has quadratic asymptotic complexity. However, there is an algorithm which is quite new. It was published just 2 years ago. This algorithm actually computes the Hong's bound in a linear time. So all of these bounds looks like an expensive one to be computed, because it looks like it needs a quadratic time. In fact, it can be computed in a linear time. However, as I said, this is quite a new result. It was published only 2 years ago. In fact, the first version of this algorithm was published a few years earlier, but this first version had a serious error, and the correct algorithm was published only 2 years ago. Finally, let me present one more bound for real roots of polynomials, which is Laguerre-Samuelson theorem. If you look here at the dates, you can clearly see that these two guys couldn't possibly work together. It is impossible that they cooperated. In fact, of course, they didn't. This bound was invented in the 19th century by Laguerre, and after that it was completely forgotten, and it was rediscovered by Samuelson in a completely different setting. Samuelson didn't really work with polynomials. He worked in statistics, and his formula was actually a statistical formula, but after it appeared in 1968, shortly after that it was discovered that in fact the Samuelson formula is equivalent to the old forgotten paper by Laguerre, old forgotten result by Laguerre. So now this theorem is called Laguerre-Samuelson theorem. It is quite intimidating formula because if you look at it for the first time, it looks intimidating and it may be scary. However, if we need to observe two facts about it. First is this guy here. And if you recall the previous lecture, this guy is nothing else but the mean of the roots of polynomials. This formula already incorporates the mean of the roots of polynomial. And the other thing that we need to observe is that in this formula, we have only three coefficients of f. We have fn, here, here, and here. We have fn minus 1 here and here, and we have fn minus 2. Nothing else. So this formula actually evaluates in constant time. It is not linear, it's not quadratic, it's constant time evaluation. We need to look only at the three leading coefficients of the polynomial. However, the cost of it is in the assumption. This formula holds under the strong assumption that all roots of f are real. So the f has no non-real roots. So this works like this. If we a priori know that all the roots of a polynomial are real, we have very strong assumption about the polynomial, we can get a very strong result about this polynomial. So we get the upper and lower bound, because m minus is a lower bound and plus is an upper bound. We get the lower and upper bound for the roots of this polynomial, but under this special assumption. I will skip the proof because I don't have time for this proof, and again the proof is in the lecture notes. So for the proof, see the CM. As I said, the link to the lecture note is just below the movie. To conclude this part of the lecture, to conclude this section, let me mention one more result, which is again due to Hong. In order to present this result, I need to introduce another notion. We'll say that M is an absolute positive bound for the roots of f if all the roots are bounded from above by M, but not only the roots of f, but the roots of f, f prime, f bis, and so on and so on. So M is an absolute positive bound, means that it is a bound for f and all its derivatives. And the theorem by Hong, which was published 5 years ago, in 2015, says that, okay, for every formula, for every method of generating bound of polynomial, bound for roots of polynomials, we will always find a polynomial with fixed degree and fixed norm, such that for just this polynomial, this method, this bound fails absolutely. So the fraction of the bound over the maximal root can be as bad as possible. So this formula is actually very pessimistic. This result of Hong is very pessimistic. It means that for every bound there is a polynomial for which this bound doesn't really work well. Now I will present just a last example. This example illustrates two things. It illustrates the different bounds that I presented today, and it also presents how important is to depress a polynomial prior to doing any computation like bounding its root. Its roots. Take this polynomial with such big coefficients. If we look at the coefficient at x cubed and we recall the previous lecture, when the mean of the roots is 400 over 4 and change the sign, so the mean of the root is 100. So we can depress the polynomial just shifting the roots by 100, and the depressed polynomial looks like this. So as you recall the previous lecture, the depressed polynomial is just the graph of a depressed polynomial is just the graph of f but shifted, in this case to the left, by just the mean of the roots. This is degree 4 polynomial, so we can actually explicitly compute the roots, and these are the roots of this polynomial. So you can see that there are 4 roots, all of them are real. 2 roots are closely clustered, the distance between them is very small, and that 2 roots are quite farther away. So the 2 roots sit here, and these are the 2 other roots. So after shifting, the 2 roots are nearly 0, and these are the 2 other roots. So the biggest root is this one. It's 114. And we can compute the different bounds for the roots. Both here we compute the bounds for the roots of f. Here we compute the bounds for a root of g plus the plus this 100, this mean of the roots. So to understand this third column is just the mean of f plus bound for roots of g. So if we, as you see, if we compute the first Cauchy bound, this for the roots of f, this is the maximum coefficient plus 1, so this bound is absolutely bad. This is the maximum root, and this is the bound. We see that it's really bad. But if we just depress the polynomial and we compute the bound for g, then this bound is 201, plus this mean we have 301, so this is much better than this one. This is much better than this one. If we compute the Cauchy bound directly at f, the second Cauchy bound directly at f, we have 1600, which is still bad. But if we first depress it, we compute the bound. The bound would be 20 times the square root of 2, and we add this mean, so we have a bound 128, which is quite good, because if the maximum root is 114, the upper bound 128, it is a really good bound. And now the more modern bounds, if we compute the local max directly at f, we have upper bound 800. However, if we first depress f, we compute the bound would be 20 plus this mean 100, so we have 120, which is even better than the previous one, and it is really good bound for the roots. The Hong's bound, again, for the undepressed polynomial, it is the same as the local max, and for the depressed polynomial is the same as the Cauchy bound. Finally, we have observed all the roots are real, so we can use the Laguerre-Samuelson bound, and this is definitely the best of all the crowd, because the upper bound is 117, which is really close to 114, and the lower bound is 82. And if you look here, the lowest, the smallest coefficient, the smallest root was 85, so 82 is really close. So this table not only illustrates how the distinct bounds behave, but it also presents, it also shows the phenomena that it often counts to first depress a polynomial, then compute the bound for the depressed polynomial, so for a polynomial whose roots are um, centered at 0, and then add back this mean of the roots, because the results, as you see, are much better than if we operate directly on the undepressed polynomial. Really, the depression of the polynomial improves, most of the time improves the quality of bounding. However, it is not that it always works, but most of the time it works, so most of the time it really is advantageous to first depress a polynomial prior to computing the bound. The second part of today's lecture is devoted to the problem of counting and isolating roots, real roots of a polynomial. So the problem is the following one. We are given a polynomial and we want to know how many roots of this polynomial sits in a given interval. One of a special case of this problem is how many roots of a polynomial sits in the interval minus infinity plus infinity. So this is a question how many real roots f has in total. Of course, we want to count this root without finding them. So the question is how many roots sits in this interval, and we want to know the answer without actually computing these roots. And the second question is to find intervals such that every interval contains just a single root. So such intervals isolate roots of f. Of course, these two questions are equivalent, because if we can count the number of roots in a given interval, we can always recursively subdivide this interval into halves and count the roots in every of the two halves. Actually, this is exactly what we will do at the end of this lecture. On the other hand, if we are able to isolate roots, then we can construct intervals that isolates roots. It is enough just to count how many intervals we have, and then we have a number of roots in a number of real roots of f. So as you can see, these two questions are actually equivalent. There are a number of methods for solving this problem. On this lecture, I will present the most classical one, which is Sturm theorem. In order to introduce Sturm theorem, I need to introduce the Sturm sequence first. The Sturm sequence is a finite recursive sequence of polynomials constructed in the following way. The first one, S0, is just our original polynomial f. Then S1 is the derivative of f. So these are just the first two terms of the sequence. And every other term is just minus remainder of the division of the previous two terms. So S2 is the minus remainder of S0 modulo S1, and so on and so on. And we continue this process till as long as the polynomials are non-constant. So once we arrive at a constant polynomial, we stop. So this is a definition of a Sturm sequence, and this definition can be directly converted into an algorithm. So the algorithm works like this. It takes a polynomial f, it produces the Sturm sequence. First, we compute the first two terms, f and f prime, the derivative of f. And as long as the current term is non-constant, we just compute the remainder of the division sk minus 1 modulo sk. On the first lecture, I explained how we divide a polynomial, so this is just executing the algorithm that we learned at the first lecture. And then the next term is minus the remainder. We just change the sign of the remainder and we append this guy to the sequence, and this produces the final sequence. Let me show you an example how it works. So let's us take this degree 4 polynomial. So this is the first element of a sequence. This polynomial is S0. So if we just compute the derivative of this guy, we got 4 times x cubed minus 12x squared and nothing more. So this is the second element of our sequence. Now the third element is just the minus remainder. So we divide this guy by this guy. So this guy is 4x cubed minus 12x times 1/4 x minus 1/4 plus a remainder. So this is a remainder of a division, hence minus this remainder is the next term of our sequence. And again, to compute the next term, we just divide this guy by this guy. We divide this guy by this guy, and the remainder is 8 over 3x minus 8. So minus the remainder is the next element of our Sturm sequence. And we repeat this process one more time. So we divide S2 by S3. We divide S2 by S3. We arrive at the remainder 25. So minus 25 is the last element of our Sturm sequence. So the sequence consisting of these 1, 2, 3, 4, 5 polynomials is the Sturm sequence of this degree 4 polynomial that we had here. Now, one more term that we need to introduce is the number of sign changes that we will denote var of a sequence. Assume that we have a sequence of polynomials. This will be finally the Sturm sequence, but the definition works just every sequence of polynomials, and we have some element a of some real number a. By var of f of a, we denote the number of sign changes of the sequence of values of these polynomials when we evaluate all these polynomials here at this given a. Again, let me show an example. Actually, this will be the continuation of the previous example. So in the previous example, we computed this Sturm sequence, and let us take a equal 3. So if we evaluate every polynomial at 3, so we will have the first one, S0 at 3 is just 3, 4 minus 4 times 3, 3 plus 2. So this is 81 minus 4 times 27 plus 2. So this 81 minus 108 plus 2. So this is 83 minus 108, so it's minus 25. So this is this guy. And analogously, we evaluate all the remaining polynomials at A, so we arrive at these guys. And let me show you how many sign changes are here. We ignore zeros, so we concentrate only on the real sign changes. So we have one sign change here. We go from minus to plus, and we have another sign change here. We go from plus to minus. So in total, in this sequence, we have just two sign changes. So var of s at 3 is 2. We have two sign changes here. So now we are ready to present the Sturm theorem. The Sturm theorem says that if we have a square-free polynomial and we have two endpoints a and b, such that a is strictly less than b, they can be either real numbers or plus or minus infinity. It doesn't matter. If we take minus infinity and plus infinity, this Sturm theorem will work just for the real line. It works equally well for a real line or for an interval. So we have a polynomial, we have an interval, possibly the whole real line, and we compute the Sturm sequence of this polynomial. If we assume that the endpoints are not roots of our f, then inside this interval, so between a and b, f has precisely this number of roots. So we compute the number of sign changes in the Sturm sequence at the left endpoint. We compute the number of sign changes of the Sturm sequence at the right endpoint, and the difference between these two numbers is the exact number of roots of f inside the interval a. I don't have time for proving this theorem. The proof is quite long. It's not difficult. It is just quite long. The explicit proof can be again found in the lecture notes. Here I will present just a sketch of the proof so you know what kind of arguments are involved here. So the proof consists of just 4 steps, 4 lemmas. So I will present only these steps without proving these steps. First of all, we need to prove that the two consecutive elements of the Sturm sequence cannot have a common root. So if something is a root of one of some, say, sk, so assume that xi is a root of sk, then xi cannot be a root of neither sk plus 1 nor sk minus 1. So the neighboring elements of this Sturm sequence have disjoint sets of roots. This is the first step toward the proof of the Sturm theorem. The second step is to prove that if we consider a function on the interval ab that for every x assigns the number of sign changes in the Sturm sequence, then this function is actually piecewise constant. It is constant except possibly in the roots of f. So the number of sign changes in the Sturm sequence may differ only at the roots of f. So if some elements is not a root, so if we have some very small interval where f has no roots, then the Sturm sequence will have everywhere will have exactly the same number of sign changes. So this was the second step of the proof. The third step shows that if f has precisely one root in our interval AB, then the number of sign changes in the Sturm sequence on the left endpoint is just one greater than the number of sign changes of the Sturm sequence at the right endpoint, so the theorem holds for such an interval. And the final step of is just to prove the theorem. So this final step now, when we have the fourth step is quite easy to prove, because what we do is we isolate the roots of f inside interval AB. So we build a number of small intervals such that every interval contains just one root of f. For every of such intervals, we apply step 3. So on every such interval, the number of sign changes between the left and right endpoint differ by 1. So the number of sign changes in the Sturm sequence between A and B differ by the means of 2 only at these intervals when we have just a root of f. So the difference is at every such interval we have just a jump by 1. So in the whole interval AB we have n jumps where n is a number of roots. So this is the idea of the proof of the Sturm theorem. And as I said, in order to see the exact proof, I need to refer you to the lecture notes, because we simply do not have enough time during this lecture to prove every theorem. But instead of proving this theorem, I will present an example. This is exactly the same polynomial as in the previous example, so we continue the previous example. We have a polynomial f. We have already computed the Sturm sequence of f, and we want to know how many roots f has on a real line. So we ask how many real roots does f have. So in order to compute the number of real roots of f, we take in an interval a b, which is minus infinity plus infinity. So we evaluate this Sturm sequence at plus and minus infinity. So if we evaluate every polynomial at infinity, so here we have infinity. This tends to infinity when x goes toward plus infinity. This again, the leading coefficient is positive, so this tends to plus infinity. This again tends to plus infinity, so we have plus infinity, plus infinity, plus infinity. This tends to minus infinity, and this is minus 22. So we have plus infinity, minus plus infinity, minus infinity, and minus 25. So we have just exactly one change of sign here. On the other hand, if we evaluate this polynomial at minus infinity, then we have the even power here. So at minus infinity, this tends to plus infinity, so we have plus infinity. We have an odd power here, odd exponent here, so this tends to minus infinity. We have an even exponent here, so this again tends to plus infinity. This here we have an odd exponent but minus here, so this is minus and minus, so this tends again to plus infinity, and this is minus 25. So here we have three sign changes, from plus to minus, from minus to plus, and from plus to minus. So all in all, at the left endpoint we have three sign changes, at the right endpoint we have one sign change. So all in all we have 3 minus 1, so 2. So f has precisely 2 real roots. So this polynomial has two real roots and a pair of conjugate non-real roots. Okay, so the next question is how many, we already know that it has two real roots. We ask how many of these roots lay in the interval 0, 1. So now we evaluate this Sturm sequence at 0 and at 1. So if we evaluate at 0, we have 2, 0, minus 2, 8, minus 25. 2, 0, minus 2, 8, minus 25. And if we evaluate it at 1, we have 1 minus 4 plus 2, it's minus 1. 4 minus 12 is minus 8. 3 minus 2 is 1. 8 over minus 8 over 3 plus 8 is 16 over 3 and minus 25. So all in all, we have one sign change here, second sign change here, and the third sign change here. So we have three sign changes at 0, and we have two sign changes at 2, one here, the other one here. So all in all, at the interval 0, 1, f has 3 minus 2, so precisely one root. So we know that f has two real roots, and now we know that that inside 0, 1, f has just one root. So one other root is somewhere outside 0, 1. In fact, comparing this result with the previous result, we see that at minus infinity we have three sign changes. At 0 we still have three sign changes. So there cannot be any negative roots. So here we have two sign changes, but at infinity we have one sign change. So f has one more root, which is somewhere above 1, between 1 and plus infinity. So the other root of f must be somewhere between 1 and plus infinity. So this is how Sturm theorem works. Now when we have a Sturm theorem, we can use it to isolate real roots of a polynomial. So assume that we have a polynomial f and some auxiliary polynomials g1 to gk. We say that a sequence of pairs of real numbers this sequence isolates root of f away from polynomials g1 to gk if, first of all, this sequence is slowly increasing, so every ai is less than or equal to bi, and every bi is less than or equal to the consecutive ai plus 1. And more important, this is an improper interval, so ai equals bi if and only if this is actually a root of f. Otherwise, if ai is strictly less than bi, then exactly one root of f is inside this interval. Moreover, these intervals are small enough that they do not contain any roots of these polynomials g1 to gk. And finally, every root of f is contained inside one of these intervals or is equal to some improper interval. So this is a formal definition of the isolating sequence, a root isolating sequence. Now, if you look at these polynomials here, in most cases, these polynomials will be just the first and the second derivative of f, because this will be needed in the algorithm used for approximating roots of polynomial. The algorithms that we will discuss on the next lecture will need an interval such that f has precisely one root inside this interval, but neither the first nor the second derivative changes sign in this interval. So in applications, This g1 to gk will be just the first and the second derivative of f. And now when we have the Sturm sequence, Sturm theorem, we can very easily isolate roots of f. The idea is summarized here. So first we find an interval that contains all roots of f. How we can do that? We just use the first part of today's lecture. So we just take a to be minus m, b to be m, where m is the upper bound for the absolute value of the roots of f. Or if we know that f will have only real roots, we can take AB to be m minus m plus from Laguerre-Samuelson theorem. But in general, AB will be just the plus and minus upper bound for the absolute values of the roots of f. Now when we have this interval, we can count the number of roots of f inside this interval using Sturm theorem. And we have three possibilities. Either inside this interval there is no root, so the Sturm theorem says that, okay, inside this interval you will not find any root of f. If this is the case, then we just return an empty sequence, there is nothing to do. Or there is just one. The Sturm theorem says that's okay, inside interval you have just one root of f. Then you use the Sturm theorem for G1 and up to Gk and check whether they have any roots. If the Sturm theorem says that, okay, neither G1 nor G2 nor G3 and so on, neither Gk has any root inside AB, so F has a root in AB, but Gi does not have any root in AB, then AB is a proper isolating interval and we return AB. In every other case, so when f has more than one root inside this interval, or maybe f has one root but one of the other polynomials also has a root here, this means that this interval is too big, is too large, and we need to split it at half. So we just subdivide its interval at its midpoint and we apply this algorithm recursively for the left and right half of this interval, and then we concatenate results of isolating roots at left and right half points of this interval. I will show you a final example. So we have some polynomial function that you can see here on screen, and we can use a Sturm theorem to count the number of roots this polynomial has on the real line. It turns out that it has precisely 1, 2, 3, 4, 5 roots. So our initial interval, which is minus 3 point something up to 3 point something, contains all 5 roots of this polynomial. So in order to isolate the roots, we split this interval at half, so precisely at 0. Now we have two intervals, the left one and the right one, and if we count the number of roots in each interval, again using Sturm theorem, we see that the left interval contains 3 roots, while the right interval contains precisely 2 roots. Nevertheless, both 3 and 2 are too big numbers. There are still too many roots in each interval, so we need to split both intervals again. So we do that, and now we have 4 intervals. The first one contains precisely 1 root, so it's okay. It isolates 1 root of a polynomial. The 2 middle intervals contains 2 roots each of them, so they need to be split again, and the rightmost interval does not contain any root, so it can be discarded. So in the next iteration, we discard the rightmost interval. We leave the leftmost interval since it already isolates a single root, and we split the two intervals in the middle. So in our next step, we have 5 intervals. First 3 contains precisely 1 root each, so they are okay. They are exactly the intervals we wanted. The first interval to the right of the x-axis, contains no roots, so it can be discarded. And the rightmost interval still contains 2 roots, so it must be splitted again. So the 3 intervals on the negative half axis will be left intact, but we need to discard one of the interval on the right and split the second one. We do it again, and we still have 2 roots in a single interval, so we again discard the rightmost interval and split the first interval in the positive subaxis. And after this step, we have 5 intervals in total, and each of them contains precisely 1 root. So this is a demonstration how we can isolate roots of a polynomial just using the Sturm theorem in combination with bisection of an interval.
That's all for today. Thank you very much for your attention. On the next lecture, we will concentrate on the last step of solving polynomial equations. Namely, when we now can isolate roots of polynomials, so we can find intervals such that every interval contains just one root. What we need to do next is to approximate the root of a polynomial, approximate this isolated root inside this interval with a given precision. So we need to find approximation of a root up to the specified number of digits. This last step of solving polynomial equations will be the subject of the next lecture, so I warmly invite you to this next lecture.